Okay, back again for Bayes. We just had a quick question about numerics on the homework. And that Bayes factor that we're going to be computing on the homework is troublesome. So writing things down on paper and computing them on a computer are very different things. I don't know if you are aware, but that is the foundations of computer science. That's how that whole field kicked off. So rounding error, it's not very exciting, but that is what computers are basically dealing with. And so lots of computational issues. 18 seconds until we've got the projector. I'll say a few things about that Bayes factor. Stephen has noticed he tried to compute it, and he said, big numerical issues, it blows up when I try to compute it. What's the issue? How would we articulate this to the rest of the class?
Like the product and then the exponential negative, that allows melting them all together and then
So we have three competing hypotheses against one hypothesis. So when you go to compute over the alternative space, so you have a point mass on three different points, and when you multiply that into the likelihood, it makes the sum of three different likelihood functions. So when you go to take the logarithm and try to log out of it, you have not just the sum or the log of a bunch of products, but you have these sum terms. And so just taking the log isn't so easy on a computer. There is an algebraic way around it, and I want you to think about it. How would you compute this? So I remember the first time I thought about this problem. It took me several hours to think of how do I actually deal with this. So I wrote down this thing I want to write. It's the right Bayesian thing I want to do. In my case, when I was doing it, it had to do with the MCMC type algorithm, where you have the sum of densities pop up. And just taking a logarithm over that is a little bit troubling. That won't fix the numerical issue, so you have to do some algebraic manipulation. I'll let you think about it. Review session is a good time to ask questions about it. I was hoping I would get asked yesterday, but nobody did, so I thought I would just leave this for this weekend. You guys can struggle through. I'll give you an extension on the homework too, so if anybody wants to ask about that on Monday's class, maybe we can have a quick discussion about it, but try to work through it and think through it, because this is the skill we're developing as researchers. So we're always going to hit all these little snags, and our job as researchers is to figure a way out, figure a way around it. So certainly, hypothetically, this is a computable problem. So you never want to compute a likelihood. You want to compute log likelihoods for obvious reasons. So the question is can you compute that Bayes factor by only evaluating log likelihoods? And it turns out the answer is yes, you can. So, and it's a little bit of algebra in there. That's one of the reasons I created that problem for you. You'll notice from more of an epistemological level, it has everything to do with we're fitting the wrong model too. So there's model misspecification. So basically our likelihoods don't fit the data. And so as you see more and more data, you start noticing that numerically. And so it creates a real issue. So anyway, I'll let you think through it. But that's part of the assignment. So extension on homework until Wednesday. You write that down. We had a productive review session last night, so I felt the energy kind of come in. So thank you for the discussion. It's better when you guys are more active. We also had a couple questions at the end about guitar playing. So I can also tell you about other things too. So Martin asked a few questions. I brought a guitar in. So, and I will show Martin how I learned to play it at the end of class. So added bonus, if anybody wants to stick around for that. Just going to be a 10-minute quick lesson. Get you started. That's all I can do. So the rest is up to you. So all you need to do is know how to start, and then the rest, there's no secrets. All you do is practice. So Martin had bought a guitar in a garage sale, and now he needs to know how to play it. And remember, experience happened to me in college, and I never learned how to play it until COVID season. So I'll tell Martin what I did. Saying that, for the rest of you, I want to tell you more about this point null hypothesis today. So that's what we're going to be discussing. So just note, homework due next. I'm going to say it like this, Friday. So I extended 2 extra days. So give that numerical problem a real shot. So I think if you can think your way through problems like this, get things implemented, that's going to make you a really terrific researcher. Okay, so point null hypothesis. This is a big issue. So I made another note last time and I said, this is the problem that everybody disagrees on. So I just want to think about some examples right here and think about maybe what the issues are. What I said last time, why this problem is so easy to disagree on, is one of my hypotheses is being evaluated at a point. So compared to the whole continuum, if theta was living on a continuum, so I'll say theta is an element of the real number. So this is just minus infinity to infinity. So this has probability mass 0 if we think about it on a continuous scale. And this has an uncountably infinite number of things in it. And so making this comparison is difficult. That's why we all disagree on this problem. It's kind of set up for it. I would say this is the most asked question in statistics. I hope we start moving away from these questions and we get to more meaningful questions. Why I don't think this is a great question is because if theta is really on a continuum, you ask me is it theta not, I'm going to say no. So let me give you an example. I don't actually have any coins in my pocket, but imagine I have a quarter and I ask the question, is it fair? So is the probability of a head on the quarter 0.5? People ask this question all the time. I've seen this written in countless statistics books. So what's the answer to that? Is the probability of the head 0.5? Probability of the tail 0.5? Is it fair? So for any quarter out there in the world, what's the answer? Alan? Probably not. How probably not? So what would you say the probability of if I did have a quarter? Just can't use quarters these days. I don't go to the store and get change from anywhere. But what do you think the probability is just in your own mind? It's a subjective question. What do you think the probability is that some random quarter that I pull out has probability of landing heads 0.5? Yeah, she wants to say 0. I mean, it's vanishingly small, and I would say it's 0. So for me, I feel pretty good at saying there's no way that the sides are equal. Now you might say, well, it depends on how you flip it too, and that's true. So we'd have to even like standardize the question and say, well, I have this like flipping machine that acts the same, but it doesn't act the same every single time. That doesn't happen. There's going to be some minute difference in a coin flipping in the air. A lot of things can change that. So it's like, what do we even mean? Is the probability even the same on every coin flip? And so we go, well, maybe we can just approximate it and think of it as an IID draw. They're not exactly, but maybe that's close enough. But what's the probability that it's actually fair? 0. Why? Because it could be anything else. Like, I'll take any of those other choices. So it could be that the coin has true probability of 0.500000002. And that's a different number than 0.5. And so maybe the question we want to ask is it close enough to 0.5 for that to be reasonable? That, however, is a different question than is it actually 0.5? So it turns out if you do flip quarters, tails comes up slightly more often. So does anybody know what quarters actually are on average? They're about 52%, 52.48. And so, it's true. Why? The coins aren't symmetric. There's more metal on one side than the other. And so, how do I know that? I don't know. I saw it in a couple books. I haven't actually done the experiment, but I know Percy Diaconis has had thousands of students flip coins and look at this to see what it really was. And it turns out it's like 52%. So, we don't really care when we play the game heads or tails, because we're like, it's close enough. So, but our question probably isn't this, is it like an actual, this one value? The answer is probably no, it's probably something different. Let me think about this more from a classical perspective. So let's just look at an example. So I'm going to say we're going to get some xi's from a normal distribution. So our old friend problem we know a lot about. And I'm going to say this is known. Make everything easy. If it weren't known, as a Bayesian, I just average over that thing and turn this into a t-distribution analysis on mu. If you're not a Bayesian, you would do something similar and you'd get that t-distribution. So you'd be dividing out the standard error, and the integral you would solve is exactly that scale mixture integral. Let's say we've got a lot of data, and I'm going to play around with n. And think about what different n means in the analysis I'm about to set up. So, Stat 101 question. We see this problem all the time. Is mu equal to mu naught? Okay, sometimes it's like 0 or something like that. Is there a mean effect? Versus something different. So not mu0. Now, every time I see this problem, I always think the same thing. It's not mu0. It's something different. That's not your question. The question is really, are you close enough to it? And that is a subjective question because you'll have to answer, what do you mean by close enough? Now, everybody is kind of in agreement on that. What does close enough mean? But the mathematical definition of close enough varies between the Bayesian and the non-Bayesian. So a typical analysis is to look at the z-score. So typically, in Stat 101, and I just mean this loosely, that first stat class you take as an undergrad, where they teach you all about p-values, they'll teach you about the z-score. Z is equal to mu, or I'll say x bar minus mu naught divided by sigma over root n. And so the idea here is to look at this test statistic, look at the sampling distribution of this test statistic under the null. So if the null were true, then x bar should be converging to mu naught. So if the null were true. So the sampling distribution of x bar would be centered at mu naught. So you look under this assumption, this is all standardized, so this should, under the null, have a normal 0, 1 distribution. So I'll write down this under the null. Sometimes you'll see people write just an h naught underneath it. This is going to be normally distributed with mean 0, standard deviation 1. So the standard error is this thing, I'm dividing it out, so it turns the scale to 1. If mu naught were true, then x bar is converging to mu naught, and this is going to have 0 mean. So you're looking at this normal 0, 1. And you're seeing how far this test statistic lives in the tails. So it turns out there's some number here and here, and by symmetry, this is just going to be the negative of the number, such that this tail probability is 0.025, and this tail probability is 0.025. Does anybody know what that number is? I'm sure all of you do.
196.
Yeah, 1.96. About. Close enough. You'll hear me say 2 a lot of times. It's 2 times the standard. 196 sounds a little repetitive. And so that's that quantile right there. And so the idea that the classicist is going to look at is if this value in magnitude, well, I guess this is the absolute value, exceeds 1.96, then you're going to reject. And the idea is that the probability of that happening would be small. It would be 5% if the null were true. So if the null were true, the probability that this score would lay over here in these tails would be 5%. So that's the p-value analysis. That's really the Neyman-Pearsonian analysis where we're calibrating an error. And so this is the fixed p-value of 0.05. If you duck that, if you duck 0.05, then you reject the null. And I'm sure we're all familiar with this analysis. We've seen this a bazillion times. And if you haven't seen it, you're in the wrong class. So this is the most common thing I see done in statistics. We sure do plague those poor Stat 101 students with this problem when we get them to like study this thing like it's an algorithm. State the null hypothesis, compute the test statistic, state what the alpha level is, and then decide, depending on the p-value that you compute, which is the same thing as seeing if this test statistic is too big, it's in the tails. So this will correspond to the typical p-value analysis at 0.05 if we use 1.96 as the threshold. Okay, so I think everybody's on the same page right here. I want to just be clear that x bar is a function of n, so I'm going to write this down that that's a function of n. And we'll see the n very clearly also here, right here. And so I want to just hypothetically ask some questions about this test statistic, the typical analysis that people do. So this is just a hypothetical mind exercise. So hypothetically, let's think about what z n. So I'll just remind us what it is, x bar n. So this is just sum of the xi's divided by n. That's what we use to infer mu. It's the sufficient statistic if you like to think about it that way, but you don't even have to think about it that way. Minus mu naught divided by sigma over ρ. And so I want to think about what this means when this thing is equal to 1.97. Okay, so let's just say I compute this for some n, and I get the value 1.97. Now all these poor Stat 101 students are like, I know what that means. That means reject, and I get full credit on my Stat 101 exam. And I get an A, and I go on to glory. And so, unfortunately, the last part's not true. So I'm going to tell you throughout a series of lectures, this is probably not strong evidence against the null, and it highly depends on what n is. And so I'm just going to make a note. Note, Zn is equal to 1.97 should mean different things. Depending on n. Now, it seems like I made a quote, so I'll just be a little bit more specific. I think this is true. I'll see if I can convince you that this is also true. That this value should mean different things to you, depending on what n is. So, just have a quick question, and we'll answer this question in a moment. If two different scientists And I'm going to be a little bit hypothetical and make up a scenario. Two different scientists are trying to understand what mu is. The same parameter that they're interested in. They have slightly different experiments. How they went out and collected data is a little bit different, but their data is able to estimate mu. So they're able to compute an X bar. These two different scientists both compute 1.97. And they have two different ends. Okay, so scientist one, so let me just keep phrasing this. If two different scientists both compute Zn, and I'll say this is scientist one, Z-score 1.97, and scientist two, and they're going to have a different end. Computes 1.97. And I'm going to say this n for scientist 2 is 10,000. And let's call this n2 for scientist 2. And n1 right here, we'll say this n1 is 12. Okay, so both scientists go out there, they're trying to figure out what mu is. They both have the same sort of hypothesis test situation. They want to both test this. It just so happens that after 10,000 data points, scientist 2 computes 1.97, and coincidentally, scientist 1, after seeing 12 data points, also computed 1.97. My question is which scientist has more information against the null? Or do they have the same information against the null? We both know that if you're a Stat 101 student, you would say, well, I don't know, you reject in both cases. So maybe it's the same. But for me, I think one of these scientists has more information against the null than the other.
But I want to ask a question, but when we first started to talk, we were talking about the probability of your mu being some close value in hypothesis mu zero. But that's not really what the test does. The test is asking, or the test is giving you the probability that your test statistic is observed under the null. So
That's
it's
right.
not the same thing. So why is that controversial?
Well, you're asking a big question. So we're not there yet. Let's just get into this can of worms a little bit more slowly. Well, Ahmed just wants to get down to it. So we have plenty of time to fight about this. So why is it controversial? I'm going to show you. I'm going to go through a series of steps of showing you what the controversy is. So one thing I can say, why is it controversial? Because a lot of people fight over it. So that's the real answer. It's controversial because there's a controversy. Now, why do I believe that controversy should exist? And I'll argue, yes, it does, and those guys are wrong. So we'll do that. You can be that other guy, and we'll see if I convince you. Maybe you convince me. We'll see how it goes.
So first, I would say my opinion about this is it depends on whether your test statistic is consistent or not.
Okay, so it is consistent in this case, just because it's all set up. So our test statistic is complete, it's sufficient, it's consistent, it's asymptotically unbiased. That's your consistency thing. It's also unbiased. So it's got all kinds of good properties. So for this problem, the test statistic at hand is about as good as you can get. So X bar for measuring mu, good test statistic. We all like that. Fisher likes it and gave us all the reason we like that. And I agree with Fisher. It's a good statistic to use. So we know the answer to that. So what do you say, now that we at least know it's a consistent test statistic, this test statistic, I don't have a problem looking at this. I think that this does have information. I'm just not sure if it's calibrated correctly. Let's answer this question. Which scientist has more information? scientist 1 or scientist 2? Let's just do a poll. So I'll ask 2 different possibilities. Scientist 1 or scientist 2. So we'll just poll everybody. Not everybody can see on camera. I am a qualified vote counter, so no controversies there. Let's just see how this goes. Who says scientist 1? Now, hold on, I want to baseline this correctly. I need a vote from everybody. So in my class, everybody has to vote. So that's how they do it in Uruguay, right? Everybody votes. So we're going to go the Uruguayan rules here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 people are just showed up today. So I need my numbers to add to 17. Who says scientist 1 has more information against the null? You put it up, like be proud. Nobody can see you except for me anyway. So Eric, is that a yes or is that a, okay, Eric says yes. Okay. So 1. This better be 16 or I'm gonna throw a fit. So let me just add one more in here. So I saw somebody else put their hand up. So 2. Okay, so how many of the other people, who says scientist 2? Okay. Oh.
Do you know, can you see the observations?
All I'm going to give you is X bar, but I'm not lying to you about the model. Okay, I'll give you the observation. Yeah, you can see it. Okay, that is everybody else. So 15 people. So people say this right here. The second person that came in was me. It said scientist 1. So this is supposed to be evidence against the null, and it only took me 12 data points to get there. This took me a lot of data points to get there. So I'm going to argue that it's really the rate at which you achieve this p-value. And so if the null is incorrect, it turns out what will happen is a function of the sample size, the p-value will be going down. It gets smaller and smaller. And it's really the rate at which it decays that's important to me. Your homework helps to exemplify that by drawing the p-value plot. So sequentially evaluating the p-value and seeing the rate of decay of that p-value.
So you're saying that if scientist 1 had more data, then we'd see a higher p-value?
If scientist 1 had more data, then I think that the p-value would cascade be much, much smaller. So I think the other direction. So I think if scientist 1, and this wasn't just an artifact right here, it really was decaying. And this would suggest maybe mu is something different from mu not. That if I had 10,000 data points right here, I'd expect that p-value to keep getting smaller and smaller and smaller.
I think that's what I know.
Let me try to explain that a little bit better. So let's just think about this test statistic is n goes to infinity. So let's do the limiting analysis. Think about it. I like to think about things this way. Let's just take it to the limit and see what happens. So again, z is x bar n minus mu naught over sigma over root n. So let's think about, and I'm gonna, now this is a perfectly hypothetical thing that we're considering. This wouldn't happen for an actual, any hypothesis. If I ended up cranking up n, this random variable would change. But I'm trying to do the hypothetical analysis and ask the question of, what does this mean right here when it's 1.97? So let's think about, so this corresponds to some p-value that's marginally smaller than 0.05. So the p-value is going to be less than 0.05. And everybody's like, yes, publication time. Hold on. So I'm going to argue over and over again, and maybe we'll understand at least where the controversy occurs. as to why I don't think it's publication time yet. But saying that, that's the culture we live in. Let's think about when n gets really big, infinity, what this actually means. So if this was some fixed value, and n was really, really big, if you don't like my n going off to infinity, just take it to a billion, trillion, quadrillion, raise it to a bazillion, whatever big number, just keep doing that. So if you don't like the concept of infinity, so just keep adding some numbers. Do it really fast, and we'll converge in our thinking. We know what this does right here. So again, our null hypothesis that we're testing is mu is mu naught versus mu naught. Mu naught, something different. Same data, set xi's coming from the normal distribution. And I get to do the thing I never get to do in practice. Let's think about that. It's not a real statistician thing because I wish. If I could have an infinite amount of data, I'll just do estimation and I'll tell you what the parameter is. So it's the problem with our thinking here. If we did have n going off to infinity, we probably wouldn't do hypothesis testing anyway. We just estimate everything perfectly. So we know what this does. This part is going to 0 for obvious reasons. If we didn't know sigma, we would estimate it. We'd have a consistent estimator for sigma, and that would be converging to sigma. And everything would work out great. This would be a t analysis, but as n started climbing really big, it would start to look normal pretty quickly. So it doesn't really matter that I'm saying I know sigma. So if I didn't, same sort of conclusions. So if this is going to be 1.97, and the denominator is converging to 0, what does this need to be converging to? Also to 0. So what does this mean when it's 1.97? It means that this is converging to 0 in the numerator 1.97 times faster than what's converging to 0 in the denominator. And if you don't understand that, go review derivatives. That's the whole little concept. So we have these two things converging to 0. What's 0 over 0? 1, right? Yeah. So it's all about the rates of convergence. So the numerator is converging to 0 1.97 times faster than this is converging to 0. But still, that's 0. So x bar n minus mu naught is converging to 0, then x bar n is converging to mu naught. Okay, so that's obvious. What is x bar n converging to in general? This is a consistent estimator. This converges to the truth. So this will converge to mu. So this is the truth. So why? Because this is consistent. So this is the law of large numbers. Central limit theorem tells us a little bit more, tells us how it's distributed around the truth. But this is just the law of large numbers. So it converges to the truth. So mu is mu naught. As far as going to mu naught from this line of thinking, and x bar converges to the truth. So mu is mu naught. And this happens with probability 1. So I would say in this case, the null is true. Now I won't conclude too boldly right there. You might think, no, the classicists, what they're saying is, while that thing is extremely close to mu naught, it's not mu naught for any fixed n, And in fact, I'm 1.97 standard errors away from it, even though it's epsilon. So X bar is really close to mu naught. So let's just scale this back and think like n is a million, a billion, some big number, trillion. I guess million's not even a big number anymore. So let's say it's a quadrillion, whatever that is. So what this says is it's actually really 1.97 standard errors away from it. And for the named Pearsonian, that's meaningful. So it's not mu naught. It's something different. But it's microscopically close to mu naught. And we usually end up with a conversation where we say, well, it's significantly different. So this is significant. We didn't say that it's not really close to mu naught. We just said it's significant. And that could mean something. I think that there are applications where it's like, yeah, I really do want to know that it's just microscopically different. But a lot of times when we talk about this problem, this wouldn't be practical to us. X bar is so close to mu naught that why would you reject it? But it is still 1.97 times 1.97 standard errors away from it. You can think to yourself if that's meaningful. So debate's not over. So we're just getting started with this. So let's just digest this for a moment. But I would say with probability 1, if somebody showed me this analysis and said Z is 1.97 and N is a bazillion, X bar is really close to mu naught. So I think it's close enough to be acceptable. So it's really, this distance is going to mean different things to you depending on who you are. Neyman and Pearson, if the model was correct, if the data really was generated like this, they are calibrating an error rate properly. So I don't have a problem with what Neyman and Pearson said mathematically. I just have a problem with the application of that. I do think that there are applications where this is exactly what you would want to do, and I think there's a lot of applications where this doesn't have anything to do with what you want to do. So we'll go down that tree as well. But for me, the probability in the asymptotic analysis, the probability that mu is equal to mu naught is 1. And the Bayesian will conclude this, and we'll get to that part of the calculation.
It seems to me that there's a trade-off between having too little data and too much data, in the sense that if I have too little data, I have a greater risk or a greater probability of observing a test statistic that is not live.
Yeah.
Whereas if I have too much data and I'm just strictly following the math, I would just reject for something that may not be significant difference.
That is what I would call a Goldilocks scenario. It's like, oh shoot, if we get too much data, this doesn't work all that well. What we do notice in practice that groups that get a ton of data, they have really small p-values all the time. And fields that just have a ton of data, like survey scientists, where they go out there and take 10,000 surveys, all their null hypotheses are rejected. It's something different than what they speculated in the first place, and they'll find that out. Yeah, there's this weird trade-off, right? It's like, I don't want too much data. So there is an answer to this in the Neyman-Pearsonian realm. You need to start out and say, I want to be able to test at a fixed probabilistic distance. So I want to be able to say, if there is a difference from the null hypothesis, maybe with probability 0.999, I want to be able to tell. And so I'm going to figure out what n needs to be so that I can tell that difference. And so that's the full-blown wall testing scenario with the power analysis. I want to point out, it doesn't seem like a lot of people do that in practice. What they do is they go and grab a lot of data, and if their p-values are small, they go to publishing count. And if their p-value is not small enough, then they go, well, now let's do the power analysis. And I'll show you I didn't have the power to actually reject the null hypothesis in the first place, so now I'm going to get more data. Here is something that's true. And this is true regardless if your null is correct or false, or if your model is right or false. It'll happen faster if your model is wrong. You'll notice this in the homework assignment that I've given you, that if you want your p-values to be small in this sort of analysis, just keep going and getting more data until eventually you go under your threshold. That will happen irregardless if the null is true or not. So if you don't have a real stopping rule, your p-values will eventually be ducking 0.05. So what happens if the null is not true, or if you have a false model, the p-value will be getting smaller and smaller as you get more and more data. What happens when the null is true? The p-value is a uniform random number between 0 and 1. We'll prove that. We've got a couple different proofs of that claim. And so a uniform random number will eventually be less than whatever threshold you pick if you just keep generating them. And so what's the probability that you've done 0.05 from a uniform 0, 1 to 0.05? So you'll do it eventually. We're going to talk about all those issues. This score right here will come up for the Bayesian as well. But they think about it very differently. So it's baselined according to the alternative, and we need to talk about that. So before we decide who's right and who's wrong and try to settle this debate, which I'm going to guess we're not going to be able to. So, but if we do, we should inform the rest of the world. So let me at least tell you what a Bayesian does and how they address the point null hypothesis. So Bayesian uses a point mass mixture for the point null hypothesis. So same situation. We'll just go back to I've got xi's coming from some model. I'll be a little bit more generic about it. We'll go back to the normal model so that we see some examples. But this is a general setup. So I goes from 1 to n. Our hypothesis is just beta is equal to some value versus it's something different. So there's a bunch of Bayesians in the world that will go out and try to answer this question, but the answer they're giving you is completely different from what the Neyman Pearsonians give you. Basically just looking at the z-score. So they're going to look at more of that. So point mass mixture prior. Looks like so. Times some alternative distribution. I'm going to write it like this. So this is the null prior. Right here. I write this down. Pi h naught given theta. So this delta function right here, this is just going to take on values 1 if theta is equal to theta naught, and 0 otherwise. And so it's a proper prior, but if I integrate it over the whole continuum, but just constrict it to the null space, which is just that point, everything adds to 1. And this needs to be proper as well. So I'm just going to have one restriction on this thing. It's just going to be the integral of this is equal to 1. So it's proper and it's normalized. And so the integral over this whole thing right here is going to be 1. Let me just tell you what this is. This is going to be the probability that h naught is true. And this is going to be the probability of h. So we discussed this all briefly last time, what these things were, and these are the components that we see in our phase factors. So that same discussion holds here, same interpretation. And so this prior looks like this. So p theta. I'm going to have some alternative. So I haven't told you what the shape is, but I'm probably probably pointing in the direction of something. This is controversial, and there can be other shapes for the alternative. So this looks like the H1 theta. And then I've got some value theta naught right here, and I placed a point mass right there. So this is my delta function. Theta, delta, theta is equal to theta. So it's just a spike right there. How much weight are we putting on this? Well, that has to do with this term right here. So the height of this is measured by that. And how much weight am I putting on this part of the distribution? It's measured by this. So the height of this thing is going to be controlled by that. How much mass do we want to put on the alternative versus the null? Now, the only thing that is really a big question in this point mass mixture prior is what's the alternative? So this is what I would consider the continuous portion of the alternative prior. It's placing mass on this part of the space. Now you might say, should I remove this little point from this alternative? And I would say, yeah, we could do that. So we could end up putting a delta function right here. Theta is not equal to theta naught. Remember, we're working at a continuum, and so if I just remove a point from a distribution, it doesn't actually change it. And so usually I don't write this down because it doesn't actually show up in the mathematics. If you did write it down, everything would work out the same. If you didn't write it down, everything would work out great too. If I integrate over just a point, it doesn't do anything. Okay, so this is the idea. I place some amount of mass on pi naught, and then I diffuse mass over the alternative space, and I place some amount of mass on that. These are going to sum to 1. So this is a positive number, this is positive. So you'll notice that this integrates to 1. So that's a proper part. If we didn't put a point mass of mass on the null hypothesis, if we treated it like a continuum, then a priori we'd be saying we have 0 mass a priori on the null. No amount of likelihood will get you away from that. So if you really want to just reject hypotheses, I'm giving you a method to do it. Use it prior that puts no mass on it. You'll reject without any data. And so these classicists work so hard by going and collecting more and more and more data, and all they want to do is reject the null hypothesis in the first place. It's not science, so let's try to think about this more scientifically. My question is, what should the alternative prior look like? And this is a big question. This is like the whole question, but we have to think about what it means. So I will say, at least for computational considerations, if I use this to be the conjugate prior, I can do the math. And so if we pick this to be conjugate, then I'd be centering it somewhere.
Push the paper.
Center, so I'll just say center, and we'll get these names next time, and then I'm going to have some variance. And so if I pick the normal family, I can work everything out in closed form, and we will do that. That's a typical analysis. It's a common analysis. There's probably other things you can do as well. So what I really want you to do is think about what it all means. Next time we're going to come back and think about what the center should be and what the variance should be. Right here. Let me just ask a quick question, and then we'll be done. What do you think this center should be? What would you think it be? We'll pick up. Okay. Some answers. Some people said theta naught. I'm going to argue that's the case next time. So think about that, and if you think it should be something else, be prepared for a reason why you think to pick something else. We'll pick up here next time. The key point that I'm going to be focusing on is this is the most influential part of the analysis, is this variance. So a lot of people think it's these terms, but it's actually this. So we need to think about what all this means and what we're doing with it. And then we need to come back and think about what if we did choose this to be the improper prior, what would happen? We would get a nonsensical result. We'll look at that as well. That's it for now, you guys. So big questions, lots to delve into. Hopefully we can solve this problem for the rest of the world. If we can't, at least what we'll be able to do is explain what the differences are between the two sides, what their objectives are. Okay, guys, have a great weekend.